Hello, my name is Emma Dickinson, and I'm an undergraduate in Materials Science and Engineering at the University of Pittsburgh, and I'm participating in the online research experience for undergraduates through Texas A&M University. This is my final presentation for summer 2020, and the project that I've worked on is the micromechanical behavior and multifunctional efficiency of composite materials in supercapacitors. I would like to thank my mentors and the U.S. Air Force Office of Scientific Research for sponsoring this project. So my project began with a literature review of supercapacitors composed of new multifunctional materials. Then I began to study multifunctional efficiency, or MFE, metrics, and how they are used to measure the multifunctionality of these systems. Then I began to work with experimental data and MATLAB code to study the effective stiffness of composites according to different theories. I was able to use this information to implement a new MFE metric and run parametric studies to see the impact of a composite's aspect ratio, loading directionality, and orientation on the multifunctional efficiency. The overall motivation behind this project is to be able to represent the multifunctionality of a supercapacitor that can be used for both structural and energy applications. The need for multifunctional materials comes from the fact that currently electrochemically active materials in supercapacitors and batteries are very brittle and cannot support structural loads. Because of this, structural materials are required to case devices, which adds to their overall weight. So with the use of multifunctional materials, supercapacitors can be used for both structural and energy applications, such as in aircrafts, reducing their weight. I studied the nanocomposite morphology of supercapacitors, comparing thin films to fiber reinforcement and noting the solid electrolyte matrix. By studying the micromechanics of these composites, we hope to address disadvantages of previous MFE metrics. A previous MFE metric I studied was from the Wetzel 2011 paper, which presents an MFE based on comparing the specific modulus and energy density of a multifunctional platform, such as structural supercapacitors, to traditional platforms which consist of monofunctional structural and energy benchmark materials. So multifunctional supercapacitor electrodes meet the mass savings criteria by having a total MFE greater than 1. While the Wetzel MFE has the advantage of simply using experimentally collected data to determine multifunctional efficiency, we want to address some of the disadvantages of this metric. The new MFE metric accounts for the directionality of loading condition of a multifunctional composite, the aspect ratio of inhomogeneities in a composite, and the anisotropy of component materials. One of the assumptions of previous metrics is that the component materials are linearly elastic and isotropic, so we are addressing this by considering the tensor elastic properties of the materials. The rule of mixtures and inverse rule of mixtures represent the upper and lower bounds of effective stiffness of a composite based on the loading conditions. To improve on the composite stiffness theory of the rule of mixtures, I use Eshelby's method to calculate the micromechanical strain-field relationship of supercapacitor composites. Eshelby's method of micromechanics was derived from the strain-field relationship in a continuous matrix with an inclusion. The inclusion omega has the same elastic properties L as the continuous matrix, and it causes an eigenstrain epsilon star. An inhomogeneity with different properties from the matrix can be superimposed with the inclusion to represent an eigenstrain due to the shape of the inclusion and the difference in properties between the inhomogeneity and the matrix. Eshelby developed the Eshelby's tensor, which is a shape factor derived from the aspect ratio of an ellipsoidal inhomogeneity, to calculate the effective stiffness of this composite. This method does not account for strain between inhomogeneities, so it is only considered for dilute conditions. With the MATLAB code I've been working on, I can vary aspect ratios to see how the change in the effective stiffness changes the multifunctional efficiency. In my initial parametric study, I calculated the structural term of the new MFE metric that compares the elastic properties of the structural material of a traditional supercapacitor platform to the multifunctional platform. The multifunctional platform consists of a solid electrolyte matrix and multifunctional electrodes, considered to be the inhomogeneities. For this study, all of the component materials were assumed to be isotropic, and their properties are listed here. The parameter that I varied was the factor of the aspect ratio of the multifunctional electrodes in the direction of the 3-axis. This range represents all aspect ratios varying from thin plates to fibers. For this parametric study, the same strain condition of a non-zero epsilon 1,1 was used for all cases. We found that in the case of the rule of mixtures, the aspect ratio has no effect on the efficiency, and these results are equivalent to the Wetzel metric. Considering Eshelby's method, the structural term of MFE is highest for the composite of thin plate electrodes, which have an aspect ratio of 1:1 to 10 to the negative 5. The trend is that increasing this factor decreases the structural efficiency term, and the lowest structural efficiency was in the case of fiber electrodes that have an aspect ratio of 1:1 to 10 to the 5. This loading occurs perpendicular to the length of the fibers. These results show that the overall MFE is dependent on the effective stiffness of the composite, and the aspect ratio of inhomogeneities in the composite affects the directionality of stiffness. To cover a wider range of supercapacitor orientations, I conducted another parametric study by varying 2 factors of the aspect ratio. This study captures the orientation of multifunctional electrodes relative to strain and compares thin films and fiber electrodes of different orientations. I used a case study of reduced graphene oxide multifunctional electrodes to conduct the parametric study varying 2 factors of the aspect ratio of multifunctional electrodes. The elastic properties used in this study are listed here, and again the same strain condition of a non-zero epsilon 1,1 was used for all cases. Note that the structural term of MFE from the Wetzel equations of this supercapacitor platform is 5.55. These results show a surface plot of the structural term of MFE versus the factors of the aspect ratio that I varied, A and B. This log scale represents a range of aspect ratios from 10 to the negative 5 to 10 to the 5, and the highlighted plane represents the preliminary study. The range of aspect ratios tested in this study is representative of thin film RGO electrodes on the order of 10 microns thickness, up to fiber electrodes with high lengths relative to their diameter. The results from the 2-factor parametric study show that the highest structural term of MFE in this range of aspect ratios is that of fibers oriented parallel to the strain direction with a value of 4.13. The next highest MFE is that of thin film electrodes oriented with their thinnest dimension in the 3 direction. This MFE term is 3.5. Under this strain condition, the lowest structural term of MFE is that of fibers oriented transverse to the strain in the 3 direction, and the thin film oriented along the 1 direction also has a low MFE. These low structural terms of MFE can be contributed to the large difference in stiffness between the multifunctional electrodes and the solid electrolyte. Under certain loading directionality relative to fiber or thin film electrodes, the solid electrolyte accounts for the majority of the effective stiffness of the composite. The Eshelby tensor demonstrates this large anisotropy based on the aspect ratio of the multifunctional electrode in the matrix. Although the material components were assumed to be isotropic, the aspect ratio of inhomogeneities in the composite creates anisotropic properties. Based on the results of my parametric studies of supercapacitor composites, it is important to consider the arrangement of electrodes relative to how the device may be mechanically loaded because of the directionality of these composites. To further study the micromechanics of these composites, anisotropic material properties can be studied to understand the effective elastic properties. For experimental calculations of MFE, a shape factor may be introduced based on composite morphology to simplify the implementation of this new MFE metric. Here is a list of my references, and thank you for listening to my presentation. If you have any feedback or questions, leave them in the comments below.